My name is Daina Bouquin, and I'm the Assistant Head Librarian of the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. And today I'm going to talk to you a little bit about tools that are useful across a research workflow, particularly useful in regards to data-intensive environments or research that involves a lot of data. So I'm going to have a little caveat that this is a very brief overview of tools, and so just know that this isn't exhaustive, but I think it's a really good place to get started, and these are some tools that I think are particularly important across disciplines. Before I get going into the details of the tools that I've selected, I also want to point out that this selection has a slant towards the open. And so I think a lot of the goal of what we as librarians are doing in regards to research data management has a lot to do with scientific reproducibility and integrity. And in libraries, we also focus a lot on access. And so more open tools are more accessible to more librarians and researchers. And I think in the end, that makes for much more reproducible science, and in the end, it's better in the long run. But there are some tools I've put in here that are not necessarily open source that are still really useful. Just know that I'm kind of scoping this so that that's more the angle I'm going at. I'm also going to be trying to focus, like I said earlier, on discipline agnostic tools and on tools that, regardless of the type of researcher in these different fields, they're probably going to be important to all members of the team. So if you're a data management person specifically, these are going to be useful to you, but they're going to be useful too if you're in the proposal writing end of it, more on the archival end. I think all of these should be important regardless of where you fit in that spectrum. However, there are some things to consider. I'm coming at this from an openness perspective, and I know that that's not always the direction we can go, so you really need to consider the culture of practice of your community and your discipline, and you want to be using tools and recommending tools and talking about tools with the rest of your colleagues that people actually will adapt, and you want to be investing your time wisely. So you don't want to go down the rabbit hole of getting really invested in a tool that's just a little above what your community is capable of adapting to. You also want to be really aware of your institution's guidelines. So if there are restrictions on what you can and should use that your institution has policies about, remember to consider those. And your funders are probably going to have particular policies that they want you to follow as well. So with all of that being like the precursor to getting into the nitty-gritty, where do we start? With tools, I think the thing that we need to recognize as being the most important when choosing a tool, it's how does this tool facilitate collaboration and sharing. So there's always going to be concerns about preservation, and there's always going to be limitations to preservation. There's always going to be limitations to what you can and can't manage throughout a workflow. But if you can take those things and make sure that they're part of the conversation about collaboration and sharing, I think that you're going to be on the right track. Because in the end, these people have to use these day in, day out, and they have to be easy to pick up and useful across the whole team. So I think the things to consider when thinking about collaboration and sharing, the most important points to me are systematic version control. So version control that is not reliant on human error. When you use things like file naming and directory structures and things like that, that's a great first step, and it's really important for internal organizational purposes. But those things are susceptible to human error in a way that a lot of these more systematic approaches just aren't. And I think that those practices evolve throughout the life of a project, and in some cases they should be able to, and they should be able to remain flexible. So having systematic version control I'll talk a little bit more about that in a second, is important. I've said over and over already that tools should be useful to many and or all parts of the research workflow. You don't want to have 10 different tools in a single research setting or something's going to get dropped. I think that you should make sure, though, that you're recording all those steps. So they're useful in all those steps, and you're recording provenance so that you can reproduce all of your workflows. And again, I mentioned citability, all of that. Those are all important, but at the top, you need to make sure everyone can actually follow along with what you're instituting. So with that, I'm going to go into some more specific examples of how to apply that way of thinking to your working environment. And so you can either recommend and help guide people to these tools, or you can use them as a starting point to understand why I'm recommending them and why they may or may not have some shortcomings for your community or for your particular project. The first one I'm going to start off with has a lot of touch points in that systematic version control aspect of this. GitHub and Git in general, usually lowercase g, is a technology that allows you to create small snapshots of your entire work environment. That if you initialize a Git instance in a directory of files, you're going to be taking small snapshots whenever you create what's called a commit. So when you're making a commit, you're just saying save everything. And so you're saving all of that. And rather than having it build up and build up and build up, you're just saving everything that changes every time you hit save, so that you've got this whole history of everything that's been done all the time, and you have very granular control of it. Git is also distributed, so you can do this on your local machine, on local projects, on your own personal files and keep it there, or you can put it up on GitHub. And so GitHub is a particularly popular repository hosting service. So a GitHub repo is just a directory of files. And so that's just all your little snapshots bundled into one really convenient place. And you can put it up on the cloud, and other people can pull it down. Other people can save a copy of it on their system. Other people can contribute to it, and there's no overwriting of anything that anyone else does. There's also, you can do this via the terminal, so you can write whole pipelines for processing large amounts of data and really integrate this into your workflow. Or you can use little graphic user interfaces. If you're not much of a programmer, there's a number of them that are always improving. And you can also interact with GitHub in the browser. So those are all the really solid benefits of GitHub as a base for a lot of these other tools that I'm going to discuss. But there are alternatives. GitHub is free if your stuff is open. And if you want to start making private repositories, you have the option to either create an educational account, and then you have as many closed repositories while you're a student, or you can pay to have things made private. With Bitbucket or some of these other alternatives that are also just Git repository hosting services, you have to pay to make your stuff open. So there's pros and cons with both, but all of them have wiki functionality. You can track issues with them. They're great for project management. And I've just put a link here to a little getting started link. It's got a high jargon slope, but I promise you can do it, and that you should pay attention to it, because it's kind of the foundation of a lot of these other tools that I think are really going to be great for yourself and for researchers. So I mentioned project management a little bit. GitHub really helps you start that pipeline and connect up all of the rest of these other issues that I've mentioned to one space. So I'm going to focus a little bit for just a moment on, once you've started tracking your code and your data, where are you really going to archive it? Because a platform like GitHub is a hosting service that has made no promises about its preservation. There are lots of repositories, discipline-specific repositories, platforms you can buy into, like Figshare, like Dataverse, and there's also a platform called Zenodo. I'm gonna recommend you look into Zenodo, but there are lots of other options out there. But the reason why I'm gonna point out Zenodo in particular is because it is a CERN project, so everything is backed up by CERN, which is great. And they've basically offered to be discipline agnostic and free in archiving the long tail of science. And so what that means is you can take your GitHub repo and you can use Zenodo to mint a DOI for all of that work that you've been versioning. And you can save and archive and preserve a snapshot of all of that code. So when you publish your paper and you say, this is the code I used for this project, you can release that code and always have it cited the way that you used it for that paper. And so that's a really seamless pipeline. And I really encourage you to look into that just so that you can have sort of building from one platform to another. Similarly, when it comes to distributing and making sure your code is well preserved and that your work is reproducible, there are platforms for kind of making sure your documentation for your code and your code go hand in hand. And it's always important to write README files, and it's always important to make sure you've got things sorted and well organized. But there's also tools like Jupyter, which was originally called IPython Notebook, but it's now useful in many programming languages. It allows you to kind of create like a lab notebook where you have your documentation and justification for what's going on with your code. You have a cell you can enter your code into, and you can run it right in the browser. And that is a really nice way to capture and bundle up and hand everything over that you've done to someone else. And it's also really great if you put your notebook up on GitHub. You can use NB Viewer for free to render all of your notebooks. So you don't have to install anything locally to actually look at someone else's code. So it's a really nice way to make what you've done very portable. There are similar features in some of the R Studio tools like R Markdown, where you can create a browser rendered version of your code with all of its documentation that are really nice. But Jupyter has some other functionality outside of just being able to be run in the browser and hand it off to someone easily. You can also use tools like Binder to take your Jupyter notebook and containerize it. So what I mean when I say containerize is you can bundle all of the dependencies for your code in with your notebook. So it's not just, okay, look, and you can walk through and see step by step what I did, and if you have all the same system set up, you can run what I've done. It's like, no, push this button and you can run what I ran. And so Binder uses a system called Kubernetes, which is a scheduler to assign a cluster to your code, and that might be a little bit over the top with that explanation, but what you really need to know about it is that it lets you take whatever you put on GitHub, add a button to your repo if there's a Jupyter notebook in there, and you just make it so you can push that button and anyone else can reproduce your work. The best example that I've seen of this happening, there in astrophysics, there's this whole thing called gravitational waves. There's a big announcement out of a very large research group called LIGO, a very major discovery, very pivotal to the future of the discipline. And anyone can run their code because they've bundled all their stuff up with Binder and Jupyter notebooks. And so that's really powerful. Containers in general are really powerful. I can touch on those a little bit at the end, though. When it comes to distributing your code, making it shareable, archiving it, making sure you're building all of these things into your regular workflows, I think it's really, really essential to know that licenses are important and that a great tool for making sure that you're thinking through your license choice options is just chooselicense.com. GitHub has this built into their platform when you open a new repo. More and more platforms are starting to integrate this. It's like a decision tree that'll help you actually determine what intellectual property concerns you have and what you can and should do with your code, and it gives you examples of other companies that use those different licenses. And so I encourage you to check that out. And aside from all of the actual workflow of analyzing and processing and versioning your code and making it so you can cite it, there's also the publishing planning stages. And these are tools that I think are useful independent of whether or not your work is particularly data intensive. But in data intensive work, you need to make sure that you're as collaborative as possible. Remember the collaboration and sharing aspect of what I've been discussing. Online, collaborative, browser-based, LaTeX, and Markdown editors with version control are great ways to start making sure that you're thinking about all of these concepts in every aspect of what you're doing. So if you're writing a data management plan, if you're writing a proposal, a tool like Authoria is like an online LaTeX editor that anyone in your collaboration group can use. It comes with templates. Both Authoria and Overleaf come with templates for submitting to publishers. And Authoria actually integrates with Github so that you can use Github to version your Authoria notebook if you want to. So you can start building these things into every part of it. And I also just put up a link here to our Markdown because it's really foundational for a lot of the statistical communities moving forward. And our Markdown lets you actually write everything in Markdown and in R code melded together. And you can, I think it integrates Julia now too. You can render that as a PDF. You can render that as HTML. You can render it into different formats so that if you want to change something about what you're submitting somewhere else, you just change one file and you can render it different ways. So whatever part of your project you're trying to document, I encourage you to check out tools that meet these criteria. And I could go down the rabbit hole of what sort of tools you could use for analysis and visualization, but I think that regardless of the discipline you're in, there's a couple that currently you should be paying attention to. I'm focusing on things being open source because they enable more reproducibility and there's more documentation and community surrounding these tools to help you. But R and RStudio with things like our Markdown are really analysis focused and visualization focused. Python is more of a general purpose programming language that you can really go from zero to hero with if you want to. And there are integrated development environments, or IDEs, for both of those. Python has many. RStudio is really the predominant one for R right now. PyCharm is particularly great for Python. It lets you do all of your development and track all your files and all of that in one place, which is great. I'm not aware of one particularly catering to Julia right now, but Julia is another up-and-coming language that's really trying to integrate the pros of both R and Python, and so it should be on your radar for tools that you're kind of watching. And as far as manipulation goes, regular expressions. I made a bullet just about regular expressions, but when it comes to manipulation, there's always going to be packages and libraries of functions that code other people have written to help you out. So you can really just take advantage of the work done by others and the community's norms when it comes to approaching problems. But regular expressions are useful in just about any language for doing string manipulation or text manipulation. So keep regular expressions in mind when you hit like a particularly nitty-gritty problem, especially when it comes to text. Analysis and manipulation continued though. I didn't want to just give you programming tools to watch out for because not everyone's going to go out there and become a developer. I think it's important that people working with developers though learn more about those platforms and how to speak the language of developers. But if you're doing this on your own and you don't have someone else to work with you and get you over that hump, there's a lot of other tools that are really useful to you. They do, though, have some caveats. There's tools like OpenRefine, which is completely open and will help you with manipulation, and you can use regular expressions in it, and it's like a Google tool, so it's a pretty open, well-supported, not was a Google tool, but there's a community around it to give you support. These other tools are really well used in different communities like ArcGIS, NVivo, MATLAB, SPSS, but they do have proprietary platforms and costs and licenses associated with them. So if cost is going to be an issue and in the long term proprietary formats are going to be an issue, you should just be aware of them. And once you've done your analysis and munging and you've thought through how you're going to preserve this and how you're going to manage your workflow, you're probably going to want to make what you're doing really engaging. And visualization tools, there's lots of them, and a lot of the tools I've already mentioned with the programming languages already, with R and Python and Julia, they have visualization libraries. But if you want to really go another step and make interactive visualizations, maps that are really functional, you can look into tools that integrate well with those other tools. These ones in particular have APIs and they're JavaScript deployments. So if you want to make a nice online interactive data visualization, tools like Plotly, Vega kind of are their own visualization libraries that you can use using R or using Python. And there's also just D3 if you want to learn how to do JavaScript to do more web development stuff. And there's tools like Leaflet too, which are great for mapping. So if you want to do open mapping, like another thing to pay attention to. There are non-programming tools, though, available to you that are also publicly available in one format or another. So I encourage you to check out Tableau, public in particular. So you put your stuff up, make it public, it's free. Chartblocks, which is a great little like browser-based tool to help you make nicer charts in particular, so scientific charts. And Gephi. So Gephi is a lot more for network visualization, but if you're interested at all in networks, it's a really approachable browser-based tool to get you started that has a desktop application as well. And just to finish up, I think it's important to recognize that you need to bring all of these tools together in some cohesive structure and try to make sure that you're connecting things up as well as possible so you don't have like 10 tools that don't talk to each other. There are groups like the Center for Open Science who have developed the Open Science Framework, and that's available for free. It's open source to help you integrate a lot of the tools that I've discussed. And there's also just commercial platforms that focus on trying to make sure that they're doing all of this handoff for you and that they have their own tools. So tools like Globus, that is like a paid for program, but you should be aware that those things exist as well. And so with that, I think that as long as you're remembering to consider the culture of practice, the institutional guidelines, and the funder practices in making your decisions, you're gonna pick good data tools. So, thank you.